back to the dark side of the universe. So I'm going to talk about the abundance function of subhalos. I only wish that my talk is closer to Frank's talk on Tuesday, but that's fine. Don't worry, because I'm going to recap you about what Frank has told us on Tuesday. So, okay. So these are the two, I think, the most important part that I saw. Two of the most important parts that I saw in Frank's talk. And so I think the points that I want to recap are, the first thing is that there is a universality in the unevolved subhalo abundance function, which is shown in the dashed line there. And then, but when you consider the evolved subhalo abundance function, they are lower than the unevolved one. And what controls how much lower they are compared to the unevolved one depends on when the halo forms. That means it's related to the formation time of the host halo, and thus related to the concentration of the host halo. Another point that I want to just point out is that you see there is a significant scatter, halo-to-halo scatter, when you consider a single halo mass spin, right? So if you bin on the halo mass and you just look at the subhalo abundance function, you still see a significant scatter there. So in this talk, I'm going to talk about more on this halo-to-halo scatter, and then how do we characterize it. Okay, so this is outlined. I will describe the model briefly. And there are many ways you can model the subhalo abundance function. So this is just one of the ways. Frank already presented other. So I've tried to spend most of my time on the implication of this model. And as a side note, in this work, we use the simulation. We have a new suite of the Milky Way zooming simulation. We have 46 of them. They are all isolated Milky Way halos at the Elvis resolution. And then we have a few cosmological buses run by Matt Becker. Okay, so this is the subhalo abundance function that you saw here. And the color is the host halo concentration. So you can see that with higher concentration, the normalization is much lower. So we want to separate this halo-to-halo scatter from the small-scale scatter coming from the small-scale differences between halos. So we ran a certain zooming simulation with fixed large scale, and you can see the scatter is now much smaller. The large scale basically fix the normalization of the abundance. And then if you compare that with Poisson scatter, then you see it's very consistent with the Poisson scatter here. And then, now this is what Bullen-Cochrane did in 2010, and they consider the mass spin. Then you see the scatter is much larger than Poisson scatter. So we are, the basic conclusion of this slide is that this super Poisson scatter mostly coming from the differences in concentration or the formation time of the halos in a given host halo mass spin. And if you now take away of the formation time or concentration dependence, then you get this small scale scatter, which is only a Poisson. Okay, so if that is the case, then we can basically just put in the dependence on the halo concentration into the normalization of your subhalo abundance function, right? So this is just a form of fitting the subhalo abundance function. And then usually people do parameterize this normalization by only use the host halo mass only, right? So VVR is like proportional to a power proportional to the host halo mass. Now what we did here is then with this proportional constant, we now put in the concentration dependence or the formation time dependence of the host halo. So then you can characterize the normalization differences even at the given mass spin. So here it's just showing you how our model reproduced the subhalo abundance function. Again, the blue is the model prediction, the red are the actual simulation, and then this span over is just the resolution limit, and then the color from light to dark is from low concentration to high concentration. So you can see we can reproduce the scatter very well, and then this is mostly dominated by Poisson, and then mostly dominated by concentration or formation time here. And then we can reproduce this at a wide range of mass spin. This is for Milky Way halos, and this is for cluster-sized halos. Now, just a side note that we realized when we're trying to fit this, we found that the slope is slightly different between the Milky Way ones and the cluster ones. And we are not exactly sure what is the cause of this. If you have a very perfect eye, when I show the second slide of Frank's talk, you also see there's a different slope in the Elvis suite and the rest. we come up with a toy model to try to explain these differences. So we just put in the dependence on mu, which depends on the host halo mass and also the redshift. And then it works out well, but we only test this at 3 redshift and 3 mass beams. So it's still not conclusive whether this is true, but there seems to be a suggestive hint on the different slope at different mass beam. Okay, so now I already described the model, and now come to the implications. So the first thing I want to talk about is the richness mass relation. So this, people have been using this, the richness, which is basically just the subhalo count or satellite counts, as a proxy for the host halo mass. And this is a very reasonable way to do it because it scales with the host halo mass most strongly. But I want to just show you here that if you now assume a model that without concentration dependence, or with assume a model that with the concentration dependence, then how different is your concentration mass distribution ends up look like? So you can see if you now include the actual concentration dependence, you have a much wider mass differences in your fixed richness sample, and then you also have a very correlated concentration mass distribution. So this will be very important if your application of the richness mass relation you need the concentration information from this sample, because if you don't assume the concentration dependence, then your concentration estimate will be very different from the one that actually include the concentration dependence. Now, if you need a very clean mass beam, one way you can do is you can come up with some other proxy that can select out the concentration, like this is the luminosity gap. So if you only select the ones that with higher gap, then you can, in principle, select out something that looks similar to the ones that you hopeful that this only has concentration dependence. Okay, there is another implication about two-pitch fail, but Frank already did a lot of discussion on this, so I'm going to skip this. And so go back to see Frank's talk. And I just want to point out that whenever we compare the actual Milky Way to the simulation or model prediction, we need to ask what is the Milky Way means, right? It's just a halo mass or there's concentration dependence. So what is a prior is important. And we have the undergrad actually working on this, so stay tuned. Okay, so the last thing I want to say about is the halo assembly bias. So Risa, in Risa's paper and other people's paper, predicts that there's the halo assembly bias. So basically the halo counts differently as a function of halo mass and also concentration. The basic point is that paired halo usually have higher concentration, or the other way around, higher concentration halo are usually more clustered. So now we know that the subhalo occupation also correlates with concentration. So the question is, can we use the subhalo occupation as a proxy to probe the halo assembly bias, right? And actually Zenner et al., they say this is not possible. Not possible because any correlation with the concentration is too weak, so they are not likely to appear in the correlation, in the clustering signal. And this is one of the examples that you see. There is the signal in concentration, but not in subhalo occupation if you only select subhalo up like larger than 60 kilometers per second. Now, if you then use our model, because our model don't have the resolution limitation, so you can then predict the Mach correlation function down to very small velocity. And then you now start to see the signal, and there is a negative signal because now paired halo, they are more, on average, more concentrated. So on average, they have fewer subhalos. So you see this negative signal in the one halo turn, well, in the transition region actually, and they do extend to the one halo turn. So we make a prediction, say if you have a very strong, a deep survey that you can do down to like 30 kilometers per second, then you can definitely see this signal. And this signal is, I think it's very interesting because it's a distinct signal from the prediction from HODs. And also it gives you, if, for example, Frank's argument about the satellite actually go with the unevolved subhalo boundless function, that you won't be able to see the signal. So whether or not there will be the signal depends on whether the satellite actually follow the evolved subhalo function or the unevolved subhalo function. Okay, so I think my time is almost up. So I'm just put my summary slide here and take any questions you have.
Regarding the last plot,
sure.
Mach correlation function, you said this was based on the model.
Right.
But this is something you can directly check in the simulations, right? You can go to Bolshoi, for example. Check. Have you done that?
Right. So I mean, Bolshoi probably recovered down to 50 kilometers per second, but down to 40, we already see the resolution limit kicks in. So it's interesting. If you only look at resolution limit to the subhalo mass function, it's fine. But when you put in the constraint dependence, then the resolution limit requirement is actually higher.
Why does Emacs dependence come from? Why is it such a strong mass dependence?
Mass dependence?
How far down you go in terms of the Emacs?
In the
So if I only look at subhalos 60 kilometers per second,
right.
I don't see anything.
Oh, right, because you are basically dominated by the Poisson error when you select subhalos larger than 6 kilometers per second.
And to be large enough. And no, there really aren't current simulations that have been done that
Yeah. So that difference is just coming from that you are decreasing the Poisson, relative Poisson scatter.
Any other questions? If not, then we move on to the next speaker.